So there were some difficulties with problems 2.1 and 2.2, and I'm going to take this as an opportunity to show you how I would go about solving these problems. So in problem 2.1, we have some data that we want to fit with an exponential function. The exponential function is given, so we know what we're going for. The thing to do then is to use the log transform and apply it to the exponential function, and then when you do that you get this equation. It's the natural log of q as a function of time. The natural log of e just becomes 1. And so from this transform we know that we want to plot the natural log of q as a function of time. So I come down here to the data table and I'm given time and q, the flow rate. So I calculate the natural log of q just using the calculator and write the values in right here. Okay, so that's the first step. Many of you also calculated the natural log of t. It's just not needed for this problem, and you can tell that immediately by taking the log transform and seeing that the natural log of t does not show up. Okay, so then the next step is we're going to want to plot these data on the axes. And the key here is to make a plot that is accurate and clear. And so here's the way I did it. I have a plot that's the natural log of q as a function of time. And I looked here, the x-axis goes from 0 to 60. So I went along here and looked at the number of ticks that I had, and I thought, well, if I make each tick equal to 5, then I can make this 20, and so on. So I wanted to spread the range of the data along the axis as far as I could, so make the plot as big as I could. And then along the y-axis I saw that it goes from 4.76 to 5.48, and so I picked these increments. Now this is important because many of you chose to use an axis that went from 0 to 6, say. But most of that axis isn't really used for plotting. And what happens is then the data get strung out along the x-axis, but there isn't really much variation along the y-axis. And so when this happens, you really can't determine the slope very accurately. The slope is very flat and you can't really measure it. Another thing that you should notice here is I plotted the points using an X with a circle around it. The points are quite large here, they're easy to see, but they're also located quite accurately. Many of you plotted the points with a tiny little speck. It was hard for me to see where those points were, and so I couldn't tell whether you had plotted the points in the right place, and perhaps you might have even had difficulty seeing them when you drew the line. So I would recommend using a format whenever you plot a point by hand so that you can see the point easily and the point is located accurately. So when you do those two things, the most reliable way of doing that, I think, is to use an X or a cross with a symbol around it. So I plotted the points and I drew in the line here, and it fits the straight line really pretty well. So that confirms that the function is indeed an exponential function and I'm on the right track. Okay, I also labeled the axes, and so I just am being clear about what I'm plotting, because one of the things that I really want to do is be able to document what I've done, show the work, so that the person who's viewing this can follow what I've done. Okay, so now the next step is to do the analysis. We need the slope, and the slope is going to give us this term here, and we need the intercept. So I got the terms off of the plot and then did the calculations, and these are the calculations that I did, and we'll go through them. The intercept is 5.48, and that's right there. The natural log of a1 is equal to 5.48, and we get that by recognizing that the intercept is that term right there. So the term that we're after, a1, is e to the 5.48, and that equals 240, and I put the units with that term, cubic feet per second. Okay, so there's one calculation. It's contained, it's together, and it's easy to follow along this line. A2 is going to be the slope, and the slope of this is the change in y over change in x. So what I did was to go along this length, that's 65 days along the x-axis, and from here to here it's 5.48 minus 4.7, that value minus that value. And so I did that calculation and I come up with this number, and I label it with the units right away. Okay, so what I have here is the equation that I used to calculate the value, and the units. All together, single line, easy to follow. Okay, so those are the calculations, and then when I'm finished, I rewrite the equation that I'm using for clarity. I give the parameter, the value, and the unit. The second parameter, the value, the unit. And then I indicate that that's the result. I put a box around it. And then I show a check here by writing this equation out, substituting in values for x equals 40, and then I show that the value is pretty close to the given value. Okay, so what I've got here is all of the calculations that are needed shown clearly, concisely. It's easy to follow, and it's easy to tell what the answer is. So I would urge you to adopt these principles when you go and put your results together. It's not good enough just to get the right answer. You have to have the right number, you have to have the right units, but you also have to have your work presented in a way so that somebody else can follow what you did and follow what your methods were, and then also find your result and tell that that's indeed the result that you have come up with.